when he was an assistant professor at MIT. And what's really interesting when you learn about sort of the discovery and development of this field is that Ekimov and Brus were sort of working unbeknownst to each other in parallel. So Ekimov was developing these materials, quantum dots, in frozen glass behind the Iron Curtain in Russia. And Brus was sort of doing very similar science in aqueous solution in the United States. So besides these three scientists, there's perhaps a number of other people that many of us in the field would be like, oh, you know, if you were going to give a prize to more than three people, maybe there's a few others that you would recognize. So the first of these is Alexander Brus. Many of us call him Sasha. He is currently at the US Naval Research Lab, but he was a longtime collaborator with Alexei Ekimov in Leningrad. And he worked closely at those very earliest moments of the discovery of quantum dots to understand how the quantum size effects of these materials evolved from a theoretical standpoint. And there's a really awesome story that Brus first learned about Brus's work when he was called into his institute's KGB office. And the KGB officer was like, do you know of this Brus? And Brus was like, no, I don't know who you're talking about. And he handed him a package from Brus with a manuscript preprint and just a nice letter. And that was the first time that Brus and Ekimov learned of Brus's work on these quantum dots in solution. So Paul Alivasatos was, in addition to Moungi Bawendi, was also a postdoc at Bell Labs with Brus and is widely known for developing the synthesis and in particular the shape control of quantum dots. So dots don't just have to be dots, they can also be rods, they can be platelets, they can be many form factors. And you'll see some pictures of those later on in the talk. And so, yeah, Paul is widely known for those contributions. And the last person I have on this slide is Chris Murray. So Chris Murray was a PhD student with Moungi Bawendi at MIT, one of Moungi's very first PhD students. And he's the first author on this seminal piece of synthesis that Bawendi's lab put forward. And so he's widely known for that contribution to quantum dot development, as well as the self-assembly of quantum dots into beautiful superlattices, which you'll see a few pictures of later on. So I'm going to pass the microphone to Sam now to tell you a little bit about the length scale that we're talking about when we're talking about these little quantum dot objects. Okay, so quantum dots are in this category of nanomaterials, but how small is nano? So all the time we talk about nanocrystals and nanoparticles having a dimension between 1 and 100 nanometers. A nanometer is a billionth the size of a meter. So going down from things that we can easily see at a distance into more biological molecules and systems, and then down at this range above atoms, but less than things we can see in nanomaterials. And quantum dots are just one of many systems that exist at this scale. And we've actually known about nanoparticles for a long time. So gold, if you take it and reduce its size down, it goes from shiny and gold colored to red. And this is this is because we're bringing things down to the nanoscale. The properties of materials change quite drastically as you shrink below certain sizes. And this beautiful red color has actually been used in art as far back as Rome and in medieval stained glass. But at the time, they didn't know that what they were working with was metal nanoparticles. And that often comes because we can't see these. You could have a bunch of nanoparticles in solution and you would never know that that was, say, nanomaterial as opposed to an organic complex or compound. And this really comes from their size. So the electromagnetic spectrum up here, our eyes see between about 400 and 700 nanometers. And so if we look at stuff under a microscope, we can only really see stuff that can be well defined by these wavelengths. And what I mean by that is if you look at the size of, say, 532 nanometer light, or green light,
and compare that to the size of a particle that's 50 nanometers or 10 nanometers, there's just no good way to characterize it using this long wavelength. And so we actually have to turn to stuff that's much shorter wavelengths. To do that, we use electron microscopy. So this is just a diagram of a light microscope, and the same concept is used for electron microscope. You start replacing light with electrons. It ends up being quite a complicated piece of equipment, but it allows us to actually look at nanoparticles. And this has really helped develop this field. So this is an example of nanocrystals forming in solution. This is atom by atom layered growth of a nanomaterial. So we can see them form via electron microscopy. We can look at individual atoms if we have high enough resolution. We can look at assembly. And so really building up into actually looking at these materials, understanding that they are this size has allowed this field to expand quite substantially. I'm going to hand this off now to Jessica, and she'll tell you about quantum confinement.
All right. So we've talked a lot about what it means to be a nanomaterial, but the other part of what it means to be a quantum dot is that these are semiconductors. Semiconductors are one of our three broad classes of materials that almost everything can be split up into. On one end of the spectrum, we have metals, which are like copper, which are really, really good at conducting electricity. And on the other side, we have insulators like rubber, which are really bad at conducting electricity. And in the middle here, we have semiconductors, which can be good at conducting electricity if you put enough energy in first. And semiconductors are important in our everyday lives for everything from solar panels to the chips inside of our phones. And so, like Brandi mentioned earlier, Alexei Ekimov is credited with the first quantum dot synthesis. He made copper chloride quantum dots frozen in glass. And scientifically, what he found was interesting about these when he was making them was that the absorption was dependent on the size of the nanoparticles. He found that the larger nanoparticles had a redshifted absorption relative to the smaller nanoparticles. In a later paper with Alexander Ekros, Ekimov would go on to attribute this phenomenon to quantum confinement. And quantum confinement is how we get the quantum in our quantum dot title. So when you shrink a material down to the size of your electron wavelength, you start to run into this problem where your wavelength is now bigger than your material. So your electron wave function has to squish itself to be able to still fit in your material, forcing it to a higher energy than it wants to be at, and giving us a larger or a higher energy emission in our smaller nanoparticles. And that's how we can get pictures like this, with one material giving us emission in the blue, and also in this orangish yellow, just by changing the size of the nanometers. And pictures like these are synonymous with quantum dots today. It was the headline picture of every press release about this Nobel Prize. But a lot of the early work was done in quantum dots frozen in glass. And so we really have to thank Brus and his team at Bell Labs for figuring out how to synthesize these things as colloids in solution. So Brus was first synthesized cadmium sulfide nanocrystal in solution and saw a similar size effect to Ekimov in his frozen glass quantum dots. He found that as the size increases, you see a redshift in the absorption. But Brus went a step further than Ekimov and didn't just say, quantum confinement, we're good. He actually formalized the mathematical equation to tell us what we can expect to see based on the fundamental constants of the material. And so the Brus equation is the formalized equation that tells us what our band gap should be given the fundamental constants of the material, and most importantly, the radius of your quantum dot. And it's this energy of confinement term that causes the increased band gap and is the quantum confinement that's causing these particles to be of a higher band gap when they're a smaller radius. So I'm going to hand it off to Brandi now to talk a little bit about the synthesis of these materials. Awesome. So what Jessica just told you was that the colors that are generated by these quantum dots are dependent on their size. And so for these things to be useful, we need to be able to make these nanocrystals all exactly the same size. And if you've ever grown sugar crystals, for example, you'll know that this is pretty challenging. So this is looking at crystallization of just an inorganic compound. And you're seeing a concentrated solution dissolved in the solution. And what you notice is that you get these really beautiful sprawling dendrites of crystals. And what this is telling you is that you have nuclei forming over a long period of time. They're all growing at different rates, and you make these beautiful structures. But if you did this with quantum dots, that wouldn't give you anything very useful. So to be useful in some kind of technology, we need a way to grow quantum dots to be all exactly the same size in solution. And that's where Bawendi comes in. So I love this video. It has also very dramatic music. So this is one of the first videos I saw when I was just starting to learn about quantum dots as a PhD student at MIT. It was made by the Bawendi lab. And it reflects the synthesis that was originally published in 1993 by their team. So notice we're at a really high temperature, about 362 degrees. So now high we're gonna get of UV vis spectra. So we take those samples and look at them in a UV vis spectrometer, we see this beautiful continuous redshift in the lowest area of the particle. Okay, so what's going on in that reaction? So we have individual molecular precursors, they're being combined in this reaction. They're combining to form something we call a monomer. And a monomer you can think of as some unit of semiconductor. So in the case of cadselenide, you might think of the cadmium selenide unit. We really don't know what monomers look like, and we really don't even know if they exist in this kind of simple way. But this is how we normally think about the growth of these nanocrystals. Monomers combine to make nuclei, and nuclei grow to make nanocrystals. And this description of the formation of size uniform nanocrystals was actually first developed by Lemaire and Deininger in 1950. So what they described in this seminal paper is that you can control the monodispersity of your nanocrystals, of your colloids, through this burst nucleation mechanism. So what we're plotting here on the y-axis is the concentration of these monomers over time. And what we find is that if we can control the formation of these monomers, they're going to build up in concentration until you reach some critical concentration, at which point nucleation is going to happen. And then you're going to drop below that critical concentration, and you're going to grow slowly from the remaining monomers in solution. And what Bawendi did that was so special was to use this hot injection to make this burst of nucleation happen. So he injected precursors into a super hot solvent that made the nuclei all form in a burst and then grow from the remaining monomers in solution. And that is what has launched this field. So 1993 was a huge turning point for quantum dot chemists like myself. If we didn't have the hot injection synthesis, we really wouldn't be talking about quantum dots today. So I'm gonna pass it to Shaun to tell you a little bit about what quantum dots are used for.
So when we talk about quantum dots, there's a range of applications that have been developed since their initial discovery. And so we wanted to just pick a few of those. The first one here on the left-hand side is a company called Bawendi, which is a startup that uses the pure emission color of quantum dots in greenhouses so that they can more efficiently grow crops. Another example showing the widespread range of applications that exist for quantum dots are ASIO Life Sciences, which use quantum dots as fluorescent labels for bioimaging. And then kind of the last example, and probably most commercially viable, I would say, and probably even the reason that they were awarded the Nobel Prize, is the usage of quantum dots in televisions. And so here, this is a particular television from Samsung called a quantum dot OLED or QD OLED display, where they're using the pure emission color of these quantum dots as a color filter, basically allowing for more pure colors than the OLED display can alone. And kind of going along with this idea that we've really expanded in scope from this initial synthesis is the wide range of materials compositions that are available. So depending on what particular range of light we want to work with, from the ultraviolet to the visible spectrum, all the way to the infrared, there's a range of different materials compositions that can run the gambit. Another kind of way to think about the expansion of our ability to synthesize quantum dots is the wide range of different morphologies or quantum dot shapes that we're able to make. And so here you can see a series of electron microscopy images of different shapes showing that shape control. Here, pyramidal quantum dots, here elongated nanorods, ordered superlattices that can be assembled, and then finally more complex architectures like those tetrapods. Another example that kind of illustrates how far people have been able to understand and progress the synthesis is the usage of quantum dots even in undergraduate labs. And so here, this is just one example of a work where they were able to adapt the synthesis of cad selenide by lowering the temperature, by changing the reagent selection, and also the time frame in which you can complete the synthesis. They're able to adapt it to something that can be done in an undergraduate lab. And so the last thing we wanted to do after kind of summarizing what's going on with the applications is each tell you one more thing about quantum dots. And so what I wanted to tell you about is the scope of variation that you can see quantum dot to quantum dot. So even in a single batch of quantum dots, you can actually see variation between each individual dot. And so that could be in terms of the size, which we kind of talked about, the shape, the quality of the particle. And really one of the things that drives synthetic progress is our ability to understand these variations. As scientists, we need techniques that can tell us about individual properties. And so one example of such a technique is single quantum dot microscopy. And so what we can do is zoom in on individual quantum dots and study their properties rather than looking at averages. And so this is one example of kind of a video we've been able to take in lab, looking at the fluorescence behavior of these quantum dots. And what you can see without going into too much detail is there's a lot of variation in between each quantum dot, both in how the fluorescence intensity looks and how it changes over time. And so that's something that people were trying to actively research. And now I'll pass it off to Brandi.
Yeah, I each have one fun slide to share with you about something more that we'd like to tell you about quantum dots. And the one thing more I would like to tell you about quantum dots is that I just told you about classical nucleation through this Lemaire-like mechanism. And what I want to tell you is that's probably not real. So one thing that we've discovered over the last decade is that quantum dot nucleation and growth often occurs through a very complex set of chemistries. So it can grow classically in a monomer by monomer fashion, as is shown in this bottom arrow, and as was described by Lemaire and Deininger, this classical nucleation model. But more often than not, we see a variety of intermediates along the way. And we can get to a variety of form factors that require those intermediates. And so one thing we've been doing in my group that I'm really excited about is to try to intercept some of these intermediates and characterize them. And it turns out that there are some really beautiful molecules, so truly atomically precise molecules that can be isolated on the way from molecular precursors to quantum dots. We can isolate those things and characterize them and learn how the bonding in these little nanocrystal precursors looks and how to understand what that tells us about their fate as they convert to larger nanocrystals and just about the chemistry of the larger nanocrystals themselves.
Okay, the one thing that I wanted to talk about is that the science doesn't end at the surface for these materials. So we've shrunk all the way down to the nanoscale. And what that means is that we're at, hundreds of atoms, which means instead of a bulk material where the majority of them are all within the lattice, we have a lot of atoms at the surface. And this surface plays a huge role in all kinds of properties for these materials. And there are a lot of different ways that we handle the surface, and a lot of different people study them differently. So one way to do this is to put a heterostructure. So you can put another material around your quantum dot, and this can change the carrier location. So we've mentioned that you have an electron in a hole. If you have a material where the energies don't line up the same, you can actually pull one out or localize one to the center. You can improve their luminescence. This is a quantum dot under UV light that is not very bright. And that's because it's not shelled, but you put a shell on it and it gets very emissive. So this is one way that people try to improve quantum dots. They also end up being more stable over time. They don't have a bunch of stuff coming off their surface. You can also affect them in this way by adding ligands instead of a different material. So a lot of these that we've talked about are colloidal nanocrystals, which means they're in solution. And to do so, they have to have these long chain molecules. We can change those out for short chain ones that improve carrier transport and films. We can change them for more delocalizing ligands, so actually having organic molecules impact the structure of the inorganic lattice and change the conduction and valence bands. Or similar to the heterostructures, we can make a ligand shell and pull off carriers and have charge and energy transfer, which is very important for things like photocatalysis.
All right. And I just wanted to take a little bit more time to talk about QLEDs and the potential they have in our displays. So over the years, there's many different lighting technologies that have come in and out of vogue in your TV and in your phone. And QLEDs are considered one of the hottest materials for the next generation of lighting displays. They're going to be able to provide us with a wider range of colors on our screen. And the colors will be brighter and crisper, making it easier to see everything in high resolution. There's a lot of research going into making scalable application-based QLEDs at both the industrial and the academic level, focusing on everything from surface chemistry to device geometry and generally the structure. And so to wrap up this talk, we're going to take a couple slides to tell you about some of the quantum dot research going on here at the University of Washington.
So first, to wrap up and talk about the academic research that's going on in the Department of Chemistry, I wanted to tell you about the work that Jessica and I do in the Ginger Lab. And so our lab is focused on the surface chemistry of perovskite quantum dots. Perovskite is a material that's emerged pretty recently in the history of quantum dots, but has shown a lot of promise for applications because of its desirable optical properties. And so in our lab, we mostly focus on doing microscopy to get at the properties of these quantum dots, and then also on actually making QLEDs. People in the lab optimize surface chemistry and the device architecture in order to make more efficient, stable quantum dot LEDs.
Okay, so one of my groups, the Gamelin group, is also very heavily involved in quantum dot research. And this ranges from synthesizing new materials of quantum dots, a large range of them, into doping them, often with rare earth dopants or with magnetic ions. So this is taking those quantum dots and then putting in an impurity purposefully that has interesting properties. And then a lot of this talk, we've kind of mentioned time and time again that quantum dots are very interesting for their ability to absorb light and their ability to emit light. And the Gamelin group is really interested in studying that, and then also looking at how these properties and these materials behave under magnetic fields. So looking at the absorption of light, both just as is, and then absorption of light under a magnetic field, photoluminescence or emission of the materials, same thing under a magnetic field, and then also EPR, which is a magnetic spectroscopy.
Sam could have talked about our lab too. But just
I'm gonna take away from Brandi though.
so I mentioned that we're really interested in intercepting these intermediates on the way between precursors and quantum dots. And so we're really interested in this idea of building potential energy landscapes that help us to understand the richness of material evolution in that space. We're also really interested not just in these very tiny nanocrystals, but also in making nanocrystals feel physically or look physically much larger. So we're interested in the deterministic integration of nanomaterials into devices, one particle at a time. And so thinking about ways to preserve these really interesting quantum confined properties while making them physically large is an interesting challenge. We're interested very much in the surface chemistry of these materials and understanding how the surface chemistry influences the optoelectronic properties in terms of thinking about structure function relationships. And we're interested in the assembly of these materials into larger hierarchical materials, both organizing individual components as well as multiple nanomaterials into a larger macrostructure. And then finally, we do a little bit on the measurement side, but we kind of play with very simple measurement tools like electrochemistry to understand charge transfer in these colloidal quantum dots. So with that, we'll end, and we want to thank a lot of the centers that have supported this work in our 3 labs over the years and have very much been engaged in quantum dot science at the university. So the University of Washington Molecular Engineering Materials Center, IMOD, the NSF STC, and the Clean Energy Institute, as well as the Department of Chemistry. So with that, I think we'll be really happy to take questions. We have lots of glowy demos. So yeah. Please feel free. Wait, I want to, yeah, questions. Absolutely, yeah. So the idea behind quantum confinement is.
Can you repeat the question for the online audience?
Yeah, so the question was, I think I've missed something a little bit about the theory behind quantum confinement. And we kind of purposefully glossed over a little bit of the details. But this is exactly like if you've learned about the particle in a box model in physical chemistry. So when you take a material and you confine the excited electrons, the excited electrons and holes in the material. Below the size, the length scale at which the electron and the hole naturally kind of move around each other, you force those carriers into a box, which increases their energy. And so as you make the box smaller and smaller and smaller, the gap in energy between your filled orbitals and your empty orbitals starts to increase. So as you make the box smaller, that wave function is more and more squished, and that leads to higher band gaps. So you move from kind of your bulk band gap, which might be in the red, to your very strongly confined band gap, which is in intense form. Is that clearer? Fine.
They don't do that.
Early. They get that about five for I didn't think it was not for the TV set. There's a lot of people working on this, but not because of TV sets, right?
Yeah, I mean,
Or
so
did they get it because of TV sets? That would be rather.
I mean, why did Draftsman get the Nobel Prize and why did quasi-customs get the Nobel? I mean, I think we can ask this every year about the Nobel Prize. But I think as was kind of articulated by the whole panel, quantum dots aren't just about TVs. They are about these really interesting size-dependent optoelectronic properties. So, you know, take silicon, our like, you know, prototypical semiconductor material, which is the basis for all modern electronics. That material has an electronic structure which is defined in the bulk. I can't change it. I can't change the band gap of silicon. But when I go to the nanoscale, I have this really cool ability to change the homo-lumo levels of these semiconductors just by changing the size. And that opens up so many cool opportunities. So not just light absorption and emission tunability, but also opportunities for use of like bioimaging, because these things are fluidly stable, they can be processed in solution, they can be injected into organisms. They are very photostable relative to organic molecules. They have great photon absorption cross sections. I mean, the list goes on and on. They're really amazing little materials. And there's so much richness in their chemistry. There's so much we don't know about what a quantum dot is, even at the, you know, at the atomic level, that, you know, a lot of us in the field want to learn more, and we want to really know at the level of the atom how to control the properties of these materials. So, yeah. Cool.
Sure. In 100 years ago, what happens to quantum after TV like teleportation? So are they recyclable? Like what's the information?
Yeah, that's a really good question. Can you repeat it? But yeah, so the question was, you know, quantum dots are becoming sort of the de facto winner in the display industry. So we have these giant 85-inch TVs, you know, that have, you know, some milligrams of cadmium selenide or indium phosphide in them. What happens at the end of their life? Can they be recycled? Where do they end up? I think that the field of quantum dot reuse and recycling is underdeveloped at this moment in time. There is some research on the environmental impacts of these materials, both in organisms and in just the environment. It's very clear that cadmium is bad. And so there's been a huge move in the industry away from cadmium selenide. Indium phosphide is sort of a leading alternative. What happens? Yeah, I think that like many other hard technologies like batteries, for example, the future is in recycling, and future research certainly needs to move in that direction to understand better ways to recover those elements and make sure they don't end up in landfills, because that is where most of our teams.
So my understanding with these quantum dots is each one can show one individual color based on its quantified band gaps. And how do you get a working television range pixel can show a different color?
So I guess, let me just talk, so the question was, I guess, about explaining the architecture of, quantum dots in a TV. And I guess first, what makes sense to me is to start with what's currently happening in a TV with quantum dots. And so right now, quantum dots are not electroluminescent in a display that you can buy in like a Best Buy. They're what's called a QDPL display, where basically we use a blue backlight, typically I think gallium nitride, to excite the quantum dots, which are red and green, like so. And so then we use the pure color for those red and green pixels.
Green quantum dots, red quantum dots together make white light.
Yeah, and so for a TV of the future, what they're trying to do is instead of having that photoluminescent color filter effect, basically instead of having Brandi shine her light, have electricity directly injected, and then the whole thing lights up. And so, that's what they're doing here at this nanosys example. One of the biggest challenges with that is kind of engineering those individual pixels, especially when it comes to the blue quantum dots, which is kind of a bit of a materials problem relative to the red and green counterparts.
Yeah, question.
How small can you drive the box that you're forcing the plug out into?
Oh, really small, but the question is, so the question is, how small can you make the box? And at what point does it not be a semiconductor anymore? When do you cross over into being a molecule with totally discrete molecular orbitals? It's a great question. It's somewhere between 1 and 2 nanometers. I think it is different for every material, and it does depend on the structure of the semiconductor. There is some really beautiful old cluster chemistry that kind of answered that question for cadmium selenide pyramids pretty clearly. So we kind of know where that crossover is, but that crossover is also sort of dependent on which property you're asking about. Like, are you asking about the vibrational properties, for example? The size at which the vibrations look more molecular or transition from more molecule-like to more semiconductor-like is a little bit different than the size at which the optical properties make that transition. So yeah, somewhere between 1 and 2 nanometers for most materials. But it is a really cool question.
With the processes that you described in this talk so far, we talked about bottom-up synthesis for nanopigments. Is there much research into it for the bottom-up synthesis where you can laminate a larger crystal?
Yes, there is some work on top-down. So things like ball milling, for example, is a way to take a bulk material and to nanoscale it. Because the properties of these materials depend so much on the size, I think there's very few top-down strategies that would be scalable and give you that same level of size control as you get from colloidal synthesis. But don't hold me to that, because who knows what people are going to figure out in the future. Questions? Okay, well, I don't know if there's any parting words from the panel, but we really appreciate you spending some time with us. We've got lots of little quantum dot films and quantum dot solutions down here. So feel free to come shine some light on some samples. And yeah, I'll pass. Oh, and there are macarons, which are apparently like quantum dots. See, so maybe Kelly. Yeah, thanks for joining us.
I missed the first part, so can you explain?
So on behalf of you can kind of